It's time for another stage in your learning about data analytics and business statistics. And in this part of the world, we're going to think about numerical data, and we're starting to look at the big and very important question about what causes what. And this is pretty important because if we can understand, why is it that some companies are more successful than others, or some marketing campaigns work better than others, or some government policies are more effective in improving society than others, then we've got a chance to actually improve things. So this first step of that, though, is a more modest goal of actually looking for patterns and correlations between variables in data, and that's what we're looking at here. So particularly, as I say, we're looking at numeric variables, data that's measured in numbers. Excuse me, that's a key word there. So there's three pieces of tools or techniques that we're going to look at in order to help us to look at relationships between numerical variables. There's a scatter plot, which is a visual way of doing it, and then two statistical measures, correlation and covariance. How does that work? Well, first of all, the scatter plot. Scatter plot takes two variables and essentially plots one of them against the other in the x and y axis. So in this case, we've got education taken from our data set in the number of years a person has been educated for, and then on the vertical axis we've got their wages. And the reason we plot the scatter plot this way is because we believe reasonably that the more educated you are, the more likely you are to earn higher wages. So if you've just finished school, in about year 10 or 11 or something like that, chances are you're going to be a relatively low-skilled, low-paid job. Whereas if you've gone to university and got a degree, chances are you're going to be earning more income. So what we'd like to imagine the scatter diagram has is some kind of pattern to it, whereby the further up you go in the x variable, then the greater the salary is that you earn as well. So this is x and this is y, and we might expect ideally that we've kind of got this pattern here where the graph goes up in the upward direction. Okay, so the scatter diagram is a visual way of capturing that information. And it allows us to answer three questions. Is there a relationship between x and y? What's the direction of the relationship, and how strong is that relationship? So let me give you some quick examples. If I draw a scatter diagram like this, here's x and y, and the dots are all over the place. Fortunately, dots don't draw very well on this particular pen, but you get the idea. So just imagine a random collection of dots all over the place here. Then the answer to that question, is there a relationship between x and y, would be a resounding no. There's just no pattern of connection between these variables. On the other hand, sometimes you can use the scatter diagram to tell you something about the direction of the relationship. So for example, if my kind of dots are all gathered around this kind of range of values like this, this says that for bigger values of x, then I tend to get smaller values of y. So that tells us that the direction of the relationship is negative. Okay, so the more people are educated in this case, then the less they earn. Now that's unlikely, and that's certainly not what we observed in this graph. Instead, the graph that we observed in the previous page was the opposite to that. It tended to show an upward tendency for all the dots. So that says that would be a positive relationship. Now the strength of the relationship is partly captured by sort of how much these dots appear to be sort of quite closely kind of gathered in a really clear pattern, or whether there seems to be a bit of randomness about them. And that's a little bit hard to judge with a series of dots on a graph or scatter diagram, so we'll come up with some better measures of that in the covariance and correlation in a minute. And then another part of a scatter diagram which is helpful is it allows you to identify whether the relationship between x and y is linear or nonlinear. So suppose my dots look something like this. Here's x and here's y, and my dots might kind of gather around some shape like this. Now there's clearly a relationship between x and y in this case, but that relationship is clearly not linear. As x goes up, y goes up for lower values, but then it hits some kind of peak, and then as x continues to increase, then y will decrease. This might, for example, be your age and how much income you earn. When you're young, you don't earn much. As you get more experienced, your income goes up and up and up, and then you get old and your brain's not as quick as it used to be, you're not as productive as you were, and then you retire. So progressively, as your age continues to increase, then your income will go down. So that's kind of the whole story of the relationship between age and income, and it's not a straight linear one. And that becomes a little bit important to us later on when we're thinking about modelling. But for now, we're just using the scatter diagram to give us some sort of visual impressions about those sorts of things. Okay, so that's tool number one at our disposal, the scatter diagram. It's good, visual, tells you some basic things, but it's up to the judgment of people to know whether is this a clear relationship or not, just looking at some dots. So what we need is some kind of measure. So the first measure that we'll introduce is something called the covariance. And the idea of the covariance is it tells us about how different variables move together or in the opposite direction across the different values of the x's and y's. So each of the data points in my scatter diagram represents a value for x and a value for y, for a particular person or a particular company or particular country or whatever it might be. So I in this formula here represents each individual, I for individual, and as I say, that could be an individual country, an individual person, an individual company. And we have some data on x for that individual and some data on y. And what we're basically doing is taking the deviations of the x's from the mean, the deviations of y from the mean, and then we are multiplying them together and averaging those. So we add up and divide by n-1. And so that's, as it says in this little spiel down here, it's the average of this products of the deviations from the mean for x and y. And that gives us a pretty good idea about the way things work together. Best to see it in this diagram here. Suppose in this case I've got my original scatter diagram with my x and y axis, but then I've drawn another component to it, which is a red line, vertical line here, which is where x equals its mean, and another vertical line here where y equals its mean. And I'm going to and basically I've now got my dots all scattered around that. Now in this particular case you can see there's quite a clear positive relationship between x and y. The more x is, the more y is. And you'll notice that most of the dots here appear in the top right hand side of the picture and the bottom left. That's exactly what we mean when we say it's positive. Numbers in the top right are values which are big, both for x and for y. In fact, they're both bigger. The x values are bigger than their mean, the y values are bigger than their mean. So when I take x minus its mean and y minus its mean, these will be positive numbers. So these values up here, their contribution to the covariance will be basically positive because I'm multiplying a positive number by a positive number. These ones down here, the x values are below the mean, the y values are below their mean. So x minus x bar will be negative, and so will y minus y bar. When I multiply two negative numbers together, I get a positive number. So I'm averaging a whole bunch of positive numbers up here and a bunch of positive numbers down here. So the covariance will be positive, and in this case quite a big positive number because virtually all the values that go into the average are positive. Imagine a case where most of the dots are over here or down here. That's a negative relationship between x and y. When x goes up, y tends to go down. In that case, a dot, for example, over here where my cursor is put at the moment, represents an x value that's below the mean and a y value that's above its mean. So I'm multiplying a negative value by a positive value. So that'll give me a negative product. Same down here. A negative by a positive will give me a negative product. So if I've got most of my dots up here and most of my dots down there, the numbers that go to make up the covariance will be negative, and the covariance itself will be an average of all those negative numbers, and it will be negative. So a negative covariance will take place when there's a negative shape to the scatter diagram. Things are sort of going in those quadrants there. Positive covariance indicates most of the dots, and more like this example here. Okay, so that's the intuition behind the covariance formula. How do you calculate in Excel? Well, there's the details there. There's just a command. We're going to calculate the sample covariance mostly because we've usually only got a sample of data. We could do the population covariance with a P instead of an S there. Hardly any difference. Instead of dividing by n, you divide by n-1 for reasons that are similar to the point that we made about variance a few videos ago. Okay, so that's how you do it in Excel. So the covariance adds a little bit to the scatter diagram. It gives us a quantitative measure of the strength and the direction of the relationship between x and y. So there's a couple of extra bits of information that we get out of this. We get something about strength and the direction. Positive covariance means a positive relationship. Negative means negative. Strength, the stronger that connection between x and y, the more clear-cut it is that when x goes up, y goes up, or etc., then the bigger the covariance will be. Okay, so that's good, but actually it's a little bit tricky to use the covariance beyond that because its actual units are a pain in the neck. Suppose I'm measuring income, in this case, measured in dollars, and education measured in years. What's the units of the covariance? Some kind of dollars times years measure, which is a bit hard to make any sense of. Secondly, the covariance depends on the units of the data. Instead of measuring my income in dollars, suppose I measured it in thousands of dollars. So if someone is earning $50,000, the x value originally might have been 50,000, now it's just 50. What difference does that make to the covariance measure I've got? Well, it changes it, and it's actually 1,000th of what it was before. So that's a bit of a pain. So covariance is okay, but a better measure that sort of accommodates all those potential sort of disadvantages is something called the correlation. The correlation takes the covariance and it standardizes it so that it's always between -1 and 1. Effectively, that's our goal. Same idea as the covariance, but make it so that by dividing by some things so that it's always between -1 and 1. Negative covariance will mean negative correlation, which means when x goes up, y goes down. Positive covariance will mean positive correlation, which means when x goes up, y goes up. But now we've got some idea about how big by talking about how close it is to 0 versus how close it is to 1. Beauty of that is it doesn't matter what the units of x or y are, the correlation remains the same. Okay, so that's the measure that's far more useful to us. And to be precise, here's some examples of what correlations might look like. In the first example, you've got positive correlation, clearly, when x goes up, y goes up. And this is a case where the correlation equals 1. Okay? There's perfect positive correlation. When x goes up, y goes up perfectly in a linear way. So correlation is capturing the linear relationship between x and y. And in this case, there is a perfect linear relationship, so you get a +1 for your correlation. Over here, there's also a perfect correlation, but it's negative. So the correlation in this case is -1. When x goes up, y goes down, and it follows a perfect linear correlation. So those are two extremes. Here is a case when the correlation equals 0. There's no pattern at all to this data, and the correlation is just telling you that there's no relationship at all between x and y. So there's one extreme, there's the other extreme, and there's the one smack in the middle. And most commonly what you get with a set of data is perhaps something like this example here. I've got clearly a positive correlation. It's definitely not just chaos like this one, so it's bigger than 0, closer to 1, but it's not perfect correlation like this one, and it turns out this has got a correlation of 0.85. Okay, so that's a positive correlation of 0.85. If it was downward sloping, it'd be a negative correlation of a similar magnitude. Okay, so that's what you do is when you're looking at correlation, you get used to sort of looking at a number, looking at a scatter diagram, looking at a number and saying, yep, that's a very strong positive correlation, etc., for example. Okay, so correlation is a pretty useful tool to us in terms of judging. Here's the formula for correlation, and it's a bit messy looking, but at the end of the day, with a bit of work, look at the last line of this screen. You'll be able to work through this in the course notes better than I can do in a video, so I won't go through the detail of it. But the key point is the correlation takes the covariance and divides by the product of the standard deviations of x and y to make sure that the value lies between -1 and 1. That's the scaling that I referred to earlier, so that we can interpret the value. That's the main message for you to take out of that. Okay, so we calculate the correlation with this this command here, correl. Here's the values of x in this column and the values of y in this column, and that's the correlation that we get, how we get the correlation. Here's a couple of diagrams, by the way, scatter diagrams where the correlation doesn't work very well. The reason it doesn't work too well in these cases is because in both cases the relationship between x and y is not linear, and the correlation is designed to capture linear relationship. So here There's a little bit of linearity in the relationship, but there's also some data points that don't fit the linear thing at all. So the correlation will actually be not very good in this case, even though there's quite clearly a pattern of relationship. It just doesn't follow a straight line. It follows a curve like that. And here's an even more extreme example where there's clearly a relationship between x and y, which follows something like this, but we don't see that showing up in the correlation because the correlation is trying to effectively stick a straight line through that data, and there's a pretty dodgy straight line that's going to try and describe that data. So we don't get a very good correlation. We get a very small correlation in that case. Okay, so it's got its limitations. It's not applicable in those cases. It's only applicable when you've got linear kind of pattern to the relationship between x and y. Okay, thank you.